In this video we'll discuss Landau's theorem on scores in tournaments. We're going to start with just a little lemma that is going to turn out to be convenient for this. So we've got some integers k and n, k between 0 and n. Then I'm going to say that n choose 2 is the same as k choose 2 plus n minus k choose 2 plus k times n minus k. So proof of this, well, one way you could do it is just sort of, there's a very simple formula for n choose 2, and you could just substitute that in and expand everything out, and you just check that it works. That's not terribly illuminating though. So instead we'll do a kind of bijective proof. Let n be a set of size little n. K is going to be a subset of n of size k. And I'm going to put L is the rest of the set n. So size of L is going to be n minus k. Then n choose 2 is the number of subsets of size 2 in your set n. K choose 2 is the number of these is both elements in k. And when you've got both elements in k, you've just got a subset of size 2 in k, and the number of subsets of size 2 in k is k choose 2. And similarly, n minus k choose 2 is the number of these subsets of n with both elements lying in L. And k times n minus k is these are the numbers with one element in L. There's one element in k and one in L. Right, that's as if you've got you want to choose a set which contains one element from k and one element from L. You've got k choices for the element from k and n minus k choices for the element from L, and there's no other constraints. So that's nk times n minus k is the number of possibilities. And so we're just putting all these together. It's clear that this first number here, the number of all subsets of size 2 in n, there's just these are the only three possibilities. You can have both elements in k, both elements in L, or one in each. So that proves this lemma. Okay, so now suppose we've got a potential score sequence. So what do I mean by that? So a potential score sequence is a list, say S1 of a list of non-negative integers in descending order. And the sum, all the entries, are supposed to be equal to n choose 2. So remember, we're interested in the question of whether this such a thing might come from a tournament. In a tournament, the total of all scores is always equal to the number of the number of matches played, and if you've got n players, then there's n choose 2 matches. So you expect to have this property that the sum of the scores is equal to n choose 2. And such a sequence is realizable if there exists a tournament whose score sequence is just equal to this list here. Okay, so remember, by the score sequence of a tournament, we always mean the list of scores of different players, but listed in descending order. Okay, so we want to understand when, a kind of plausibility criterion for when a potential score sequence should be realizable, and it turns out there's kind of 4 ways to formulate the same condition. So we need to discuss that now. So for a potential score sequence S, the following are equivalent. So condition A, so we take any k of these numbers Si, is going to be greater than or equal to k choose 2. So that's a condition on any sum of any k. Condition B says not any k, but just the last k. If you take the sum of the last k of these SIs, then the sum will be at least k choose 2. Condition C says the sum of any k of the SI is less than or equal to k choose 2 plus k times n minus k. And condition D says that you take the sum of the first k is less than or equal to the same thing, k choose 2 plus k n minus k. Okay. So the proposition is that these 4 statements, they're all equivalent. If one of them's true, then all of them are true. If one of them's false, then all of them are false. Okay, so let's look at the proof of this. Let's look say at A and B. So A is equivalent to B as just because Sn minus k plus 1 up to Sn are the smallest of the SIs. Right? If you take a sum of any k things, right? I mean, if you take a sum of, obviously if A holds, then B holds, because but B is just a special case of A. And if B holds, right, then the sum of the smallest k of the SIs is greater than or equal to k choose 2. If you choose any other set of k of the SIs, then it's going to be bigger, because you're not using the smallest ones, you're using some slightly bigger ones. So it's still going to be greater than or equal to k choose 2. So that means that A is equivalent to B. And similarly, C is equivalent to D. The first k SIs are the largest ones, right? So, so certainly, C implies D, because D is just a special case of C. But if D holds, that means you take the sum of the largest k of the SIs, it's less than or equal to this bound here. And if you chose any other k of them, well, they'd be less than these ones. And so the sum of those will certainly be less than or equal to k choose 2 plus k times n minus k. And I should make clear all of these these are supposed to be quantified there. All of these statements are supposed to hold for all k. Okay. Okay. So let's look at the equivalence between between A and C. Okay, okay, so so we're going to suppose that A holds for all K. Okay, so we've got some so we've got some set of set U of indices, and we look at the sum of those corresponding SIs. We're supposing A is holds, and we're trying to prove C here. Okay. Okay, so we want to prove that C holds, so we need to check that SU is less than or equal to K choose 2 plus K times N minus K. So we put V is some of the other indices, 1 up to N, but with U removed. So A, which we're assuming, that says that because we've got a sum of N minus K of these guys, the sum is always going to be greater than or equal to N minus K choose 2. But also, if we look at SU plus SV, that's just the sum of all the SIs. So SU is going to be N choose 2 minus SV. Now we've got an upper bound, we've got a lower bound on SV, but then we're going to sort of multiply this by -1, so that changes the sense of the thing around. So this is going to be N choose 2 minus N minus K choose 2. And by the lemma that we had on the previous board, this is the same as K choose 2 plus K N minus K. Okay. Okay, so this proves so this proves that A implies C. And then essentially the same we see that C implies A. So we proved that A and B were equivalent. We've proved that A and C are equivalent, and we also mentioned by an easier argument at the beginning of this proof that C and D are equivalent. So we can get from any of A, B, C, D to any of the others. So these statements are all equivalent to each other.